and talk about heat capacities because these are important. So let's talk about degrees of freedom. Okay, if you have atoms, here's the ways you can store energy. Okay, because remember thermal energy is microscopic kinetic plus microscopic potential. Okay, so remember kinetic energy. So far we have two kinds. We had translational and we had rotational. So 1/2 mv squared, 1/2 I omega squared. We don't need to remember that for this. But here, translational, you translate along x or y or z in a straight line. Okay. Rotational is if you rotate. If you do both, then you include both. Okay. Now we also have vibrational. That goes like this. Okay. It's just jiggling atoms. All right. Yeah. Yes, jiggles per second. And then potential energy. Oh, so each of these, right, has 3 degrees of freedom because you have x, y, and z. So you can translate in the x, y, and z direction. You can rotate along your x, y, and z axis. Okay, and then you can vibrate in the x, y, and z direction. So you can vibrate like this. You can vibrate like this. You can vibrate like this. Whatever. Okay, so all of them have three dimensions. All right, potential energy. That's any type of intermolecular forces, so spring or electromagnetic, anything that has some attraction or repulsion, okay? And of course, that is times 3 because you have 3 dimensions. Okay, so all of these are 3 dimensions. So this brings us to something called Equipartition Theorem. So for each degree of freedom, right, there's an energy per mole of 1/2 RT. And R is just the 8.31 joules per mole Kelvin, okay, and T is temperature in Kelvin. So you can see that for each thing you end up with joules per mole. So a certain amount of energy for a certain amount of molecules, all right? And then each degree of freedom has an additional heat capacity of 1/2 R, okay? So that's just 1/2 times 8.31. So for instance, if you want to figure out the heat capacity, right, that's just going to be x, the number of degrees of freedom, divided by 2 times R. All right, and here's a list of our standard heat capacities. So for monatomic gases, right, monatomic gases, can they rotate really? Does it matter if they rotate? No, they're pretty much spherically symmetric, so rotation isn't counted, okay? So that means you end up with just translation. How many degrees of freedom of translation do you have? 3. So 3/2 times 8.31. Guess what that gives you? What's 3/2 times 8? No. 12. Hey, look. 3/2 times 8.31. Okay? So that's 3/2 R. For diatomic, you have, let's actually have a whole slide on here. So monatomic gases can translate in the x, y, and z direction. So you have 3/2 R. So translational times 3 looks like this. Okay. Diatomic, you can translate in x, y, and z. And you can also rotate. You rotate in this direction. You can rotate around the x. You can rotate around the y. Right? So you can rotate like this. You can rotate like this. But if you rotate like this, it doesn't really matter because it's hard to tell. So you only get 2 from rotation.
So heat capacity is C subscript V?
Yeah. Okay. That's the heat capacity for a constant volume.
Okay.
And that's the easiest one to measure because you just put it in a constant volume. So anyway, here's how many degrees of freedom do we have here? 5. Okay. CV, that should be 5/2 R. 5/2 R should give us about 20. And you'll notice for all the diatomic gases, our specific heat is about 20. Okay? It gets a little bit crazy, like vibrational motion can contribute. So like you can see for hydrogen, as you get up to higher and higher temperatures, right? So here you have what we picked, like 3/2. Okay? So if it's really cold, you only get 3/2. As you get hotter, you get to 5/2. You can get all the way up to 7/2 if you get hot enough that vibration starts to matter. Okay? So it's a little bit more complicated than what we're saying, but it depends on the temperature. And this is in the normal range of temperatures because you can see This is about 0, all right? 273, it's about freezing. If you go all the way down to, this is like really freaking cold because this is in Kelvin, okay? So this 3/2 doesn't matter too much for most cases. And then up here, this is like the temperature of the sun, okay? So it doesn't matter as much either, all right? For solids are, you can think of as the little molecules connected by like some kind of force, usually as spring force, because they can vibrate a little bit. So you have this vibrational, and you have something like elastic potential energy. These should each be times 3, okay? So that should be how many degrees of freedom? 6. So you get 6/2, and that's about 3 R. And it turns out these are our solids, and at these temperatures, you can see they all get close to like we are, except for maybe diamond. Diamond's weird. Because it has like a really nice crystal structure, and so extra weird things happen. Diamond's just made of carbon.
No, that's what I'm saying.
Because it really matters for a solid, it really matters what the structure is. If it's a gas, it doesn't really have a structure, but for solids, like if you have carbon like pencil carbon versus diamond, they behave really differently, even though they're made of the same atoms. Okay. Oh man, I think that's all we got time for today. I know you guys are crushed. The rest of this stuff is interesting but not super important, so I'll post the slides with the solutions and everything. And we'll start the next chapter on Monday. After Thanksgiving.
The Monday, right? After.
Yeah, the Monday. Yeah. It's probably gonna be take home.
Okay.
You guys have a problem with that?
No, not at all.
Because you guys have 2 less labs than the other class, so they'll have to take it in person, but you guys will probably have a take-home test for the next test. That's what we did in the lab. Oh wait, have we done that yet?
You know,
Oh, that's what we'll do in the lab on Monday.
we're in integrals now.
In bang activists.
And we're like, oh my god, I wish we would have taken this and it would the first part of physics would have made
Like
so much sense.
So much of the physics all of a sudden like the light bulb clicked, and I was like,
oh my god.
Well, that's good. It's before the final.
yeah, the final. I mean,